So welcome to the first one of the lecture series about details of machine learning, the part that I'm going to give. And today I'm going to start a little bit easy. Who has their background in machine learning? Okay, only one. Applied probability. What else then?
What is applied?
Sorry?
Probability.
Probability.
Yeah.
Okay. Okay. Probability. Okay. So mostly statistics. Okay. So most not machine learning. Then I think it's a good decision to give like an introduction to machine learning lecture. So like the topic of this lecture today will be like defining some of the like concepts and terms that we are going to be interested in the next lecture days. And let's start there. So introduction to statistical machine learning. So let's start by an example. So in most machine learning problems, so I'm going to start with supervised learning. In supervised learning, we have this case. So somebody gives us a data set of n components.
Mirror effect.
And then each of these zi's are actually a pair. X, I, Y, I. Can everybody see the board? Or?
No.
Who said no?
Data says okay, but then the symbol is completely unclear.
Maybe thicker
Is it
pens.
because of my writing or the?
Because of the quality of the pen.
So maybe let's do the. So these are Z's.
That's better.
Sorry, there's still more pens here. Keep the bad ones away. Throw them away. So you can mix them.
Okay, so Zi is actually a pair of Xi and Yi. And for instance, so we are going to call Xi as features and Yi as labels. So for instance, if we are trying to do an image classification task, so our data set will consist of some images. So let's say I'm trying to guess if there is a cat or a dog in a picture. So Xi will be like images, the pixel values, and Yi's would be like +1 or -1, for instance, +1 corresponding to a dog, -1 corresponding to a cat. So then we have these like labeled data points, and then we have a data set of labeled data points. So this is okay. So after somebody gives us this, okay. So let's just give like two examples. So the example one is the classification task. So in this case, X is an image. Image classification is, let's say, in RP. You vectorize all the pixels in the image. Right? And Yi is a label. So -1 plus. Another example would be regression. And in this case, first, let's say we are trying to guess the, I don't know, a price of a house. So let's say we are trying to develop something for the real estate. So X would be some properties of a house, its age, its size, its neighborhood, etc. House. Again, it's in RP. And yi would be, what would be yi in this case? Is price. Yeah, so and then the price would be R plus. So given a data set, now what we are trying to do in machine learning is to find a connection between these xi and yi pairs such that if I can learn such a connection, then if somebody only gives me an xi, then I can try to predict the corresponding value y. So like this is the basic goal. So to make it a bit more formal, our goal is, so we will fix a hypothesis class. So now I'm introducing these keywords. Hypothesis class such that I'm defining it with curly h, which is a subset of all the functions which are from x. So first I forgot to mention. So let's say the features are coming from some space curly x. And y's are coming from curly y data space. Then now we are going to fix a hypothesis class, which is a subset of all the functions going from the features to labels. Not all the functions, hopefully, but some functions. And then we will try to find the best age in this set, in this class, such that if I apply age on all of, like each of these data points in my data set, it will give me approximately two labels. So we will try to find some function such that if I, like given a data set S, if I apply this function on each of the data points, the prediction that is provided by H will be accurate. So this is the goal. So now we need to define a lot of things, obviously. So what is best, for instance? What is 5? So we need to define this kind of stuff. But before that, is this enough? So let's just first ask this question. So this is called the training problem. So let's say you are teaching a class and then you want your students to learn something. And then you give them some, like, I don't know, material. So this goal essentially says that you want your students to memorize everything. So like it's just like it's essentially memorization of the trainings, right? But is this really what learning is? So do you think like if we can just find the best age which fits the training set, is this learning? No. Any suggestions how to expand this? Okay, actually, what we are going to do, what we will ask the system in a way to do is this. So let's say we have a new data point, x prime, y prime. We also demand that when we find this h and apply it on x prime, the prediction should also be good. So for an unknown data point, this one is unknown or unseen, not unknown, unseen. Unseen meaning that it's for not seen in this first part. So this is, I mean, how can you expect something like this without putting any structure is impossible. So this looks like quite arbitrary. So now we need to make this like more systematic so that we can hope for some and we can hope for some reasonable outcomes by asking a reasonable question. Okay, so any questions up to this point? Okay, so let's continue then. So I'm going to restrict our scope a little bit. So instead of using a hypothesis class like this, I'm going to restrict myself to parametric classes. And as the name implies, we will denote this H as some functions indexed by a vector W such that, so this is again from X to Y, and then W is coming from some parametric hypothesis. So, W is coming from some subset of R. And this is called the parametric space. So instead of using a non-parametric function, so we are just parameterizing each function here by a vector from R. Okay, so now let's try to first focus on this first part. Let's try to formalize this. And afterward, we are going to formalize this. So what does it mean finding a best thing? So we need to introduce some notions to be able to define it properly. Okay, so now the question is, what is a good W coming from a set such that HWXI is going to be close to YI? Just rephrasing what I wrote over there. So to measure the goodness, the typical thing in statistics and also in machine learning is to introduce a loss function. We are going to do this through a loss function. I'm going to call it L. And L takes a pair of outputs and then produces a non-negative number or positive. Just a non-negative. So for instance, if I give this function the output of my prediction, this thing, and the true label, if this is low, then the prediction is good. And if this is high, the prediction is bad. Okay, so now given this function, I can measure the goodness of a given parameter value W. And then I can define an optimization problem such that I can attempt to solve it. So like what does it mean find? So find would mean like solving the optimization problem that I'm going to define now. So this is measuring the goodness for a single data point. And then we have a data set of n data points. And then we can just use the same idea for each data point. And then we can obtain the training problem. Yes, taking the average of these loss functions. and then finding the best W in this set, in the parameter space. So this is going to be our training problem. So now we defined it properly.
For fixed n, 1/n doesn't make sense.
Sorry.
For fixed n, 1/n doesn't make sense.
That's a very good point. And then we can come back to this in 2 minutes. So this doesn't change anything, right? But then maybe this can hit. Like if I take n big enough, this might go to something. So we are gonna come back to this. Any questions about this? Any other questions?
What are the assumptions on H? Do you have any?
So right now we didn't make any assumptions. We just want H to be indexed by some vector. So right now I'm just defining everything like in the full general case. But what we are going to be interested in will be neural networks, and then this H will have a very specific structure. But in the theory, I'm not going to exploit it actually. Yes.
So I assume you can adjust this slightly if you think that your training data might contain rather a lot of deliberate lies.
They have what?
You can adjust this slightly if you think your training data might include deliberate lies.
Like outliers?
No,
Corruption.
or indeed more than corruption, misinformation.
Well, that question goes to robust estimation part. So right now we are going to assume that the data set is very nice and everything. So right now there is no problem. So any other question? Okay, so now we define this first part, and now we need to define the second. So what do we mean by if somebody gives us some unseen data point? We also want this predictor to work well. So what does it mean unseen point? It will be too arbitrary, like what? Like we need to make a lot of clarification. So at this point, we could make this question too formal. Now we are introducing some statistical notions. And what we are going to assume, and this is in the heart of statistical learning theory. And this can be very questionable, but a lot of things are based on this assumption. So we will assume that there exists a distribution, like probability distribution. Let's say mu z on z, which is the Cartesian product of features and labels. And we will assume that the trait like zi comes from this mu z in an IID fashion. So I'm going to assume, this is the main assumption in statistical learning theory. I'm going to assume there exists a distribution and my data set is just an IID sample coming from this distribution. So then if this is the case, then I can try to formalize what I mean by unseen data points. So if I just assume that the data set I considered Z1 to Zn are coming IID from this set, then an unseen point could be, let's say, Z prime. So Z prime is X prime, Y prime. Will be another point coming from the same distribution. So right now we have like a lot of structure. So it's a non-arbitrary point. The moral of the story is that like we first draw n samples from some unknown distribution. We want to find some predictor, and then we want this predictor to work as well on some other points which could be drawn IIT from the same data distribution. This is the failure. So now by using this formalization, I can find population risk, which is going to be the minimization of the population risk is going to be our ultimate goal. So let's say our ultimate goal. So we define the expectation of this loss for a given W. We take the expectation of this loss with respect to Z. So I need to define some notation here. Sorry about this. So as a shorthand notation, I'm going to use this notation now. So this is going to be the same as loss of HWX Y. Okay, so X and Y give you Z and W is coming here.
What is the lowercase e z? What is z?
So Z is
Lowercase e z. What is the meaning?
Subscript on the expectation.
No, but when subscript, yeah, is a random variable, it's strange.
so this is
I would say mu.
we can say mu, but like since there are two variables, I want to make sure like it's taken over this. But yeah, so like the moral of the story, we have expectation with respect to Z, and Z is coming from mu Z.
User acts on the cross product.
Exactly.
And then this expectation acts on one variable.
It's again on the cross product, so like it's like each Z is a tuple.
Okay.
So you take the
Yeah, okay.
so this is the same as taking Z mu Z of this function, but Z is X and Y.
Okay.
Any other questions?
So do you really need to assume that the eyes, they come from the same distribution?
I mean, do I really need? I don't know, but if I assume it is easier.
Well, it doesn't make any difference as far as the procedure is concerned. The only difference it makes it, you can say then the training loss is an approximation to the population loss. But it doesn't make any difference otherwise.
But then we are going to try to estimate their difference actually. This will be our goal.
Sure, but of course, but
Like for
Not at this
minimization,
stage.
for the algorithm to work, no. But like in terms of like giving theoretical guarantees, then something like this is useful. Yes.
So is your ultimate goal just to evaluate that expected value or also to minimize it as well?
Sorry. So like it's not finished yet. The ultimate goal is to find the minimum of this. Okay, so this is actually called the population risk. This function. So
Minimum.
sometimes called with like denoted by R of W, population risk. And then we want to find the W which minimizes this. Because this is an expectation. I mean, we can also see this as like if there was infinitely many zi's, and then we take the average of them. So like in this case, this 1/n makes more sense. So you can like infinitely many xi, yi pairs coming from the same distribution. As n goes to infinity, this converges to this. So if, I mean, I'm saying these things generously, but like under certain assumptions, etc. Question?
So question, so if you, yes, I continue with Jan's question. So if you remove this IID assumption, the setup is the same as if you do a regression models. It's 1-to-1.
Yeah.
Yes.
There is no difference in terms of when it comes to practice,
Yeah.
but then we will try to give some guarantees on this quantity, which we can never compute because of this expectation. So we don't really know what this distribution is. This quantity is unknown, but then we will try to compute how far we are from this population risk only when this problem can be solved. So then this kind of IID assumption is going to be useful to link these quantities. All right, so let's continue then. So if we started from this step, so let's say I forget about what I described in the earlier part. So let's say I present this problem saying that, okay, I have like a data distribution, data is coming IID, and then I want to minimize this. So this problem would be impossible to solve because we make this assumption and we have no idea like what this distribution could be like. For instance, what is the distribution that gives you pictures of dogs? So like since you cannot evaluate this, and then if you see this data set as an IID sample coming from this distribution, so one thing that you could do to make this problem more practical is that you can just replace that expectation with the sample average, right? And then if you replace that expectation with the sample average, what you obtain? You obtain exactly this. Again, so like we came back to the training problem. So if I replace this expectation with the average over these data points, like the loss function that applied on the points, and then we take the average, it's exactly this. And then now we see this in this training problem after defining the population risk and then replacing the true expectation with the sample average. So in statistics, this is called, and actually I'm going to use this new notation for this function. This will be L of WZI, right? X, I, Y, I, they form ZI, and then this is L of WZ. And this is called the empirical risk. And the minimization of this problem is called empirical risk minimization. And ERM is one of the biggest keywords for machine learning. Okay, so since we make this IID assumption, this IID assumption is going to be useful for several reasons. So let's go back to like what's happening in practice. So somebody gives us training set S. By trying to minimize this problem, we obtain some W. And then afterwards, we want to hope, even if we get like zero training loss, zero empirical risk, our ultimate goal is this. So we want to know, we want to have an understanding, even if we solve this perfectly, it might not be solved perfectly, and this is not going to be solved perfectly. And then how much error we are making. So then I would want to have an idea about what this population risk, what is the population risk associated with this estimated W, which was estimated only by using the training set. So this is going to be a problem. Because if I'm just getting like zero training loss, but if my population risk is like super huge, then there is no point. It's the useless parameter. So, but then I want to have an understanding of this. Like in this case, it's called overfitting. You are fitting data points very well, but then if there is like an unseen data point, you cannot predict it properly. So this is overfitting, and then we want to avoid this. And one way to avoid this is to properly estimate what would be the population risk. So, any opinions? The next days we will be essentially working on this quantity and linking it to heavy tails and fractals. But as a start, any idea how to estimate this? So let's make this problem a bit simpler. So let's say we have a parameter set which is finite. Parameter space. So it contains finitely many points. And in this case, can we estimate RW somehow? Like this is going to be our ultimate goal. And then I want to motivate that I'm going to present at this point.
So you're estimating RW for every W or just RW star?
So W is given to me somehow.
Okay.
It doesn't need to be anything. It just comes from this set.
Okay, it doesn't need to be necessarily the minimum.
How can I do any suggestion? You can split the data without splitting the data. So like just like mathematical terms.
Some adversarial approach.
Just mathematically. Like can we estimate this by decomposing this to some terms and then bounding one of them, something like this. Also, I forgot to say this is denoted as R hat and W, this function. Okay, so let me give you a hint.
What is the goal? So you want to take R hat, add and subtract R hat?
Yes. Okay, so this is R hat and W plus I think everybody would agree on this. So most of the bounds in machine learning are based on this decomposition. So the idea is this. So I want to estimate this quantity. This term is the empirical risk, and I can compute it because, like, even if I don't know what the value is exactly going to be after the training procedure, since I have the data points, at least I can evaluate them on the computer. So I can numerically compute them. So this is computed. Numerically computed. And then this term is called the generalization error. Or sometimes called generalization gap. And it essentially measures how different the population risk from the empirical risk. So if they are very different, then my algorithm does not generalize. So like the estimate, like the empirical risk that I find by my procedure is so much different than the population risk. So I'm not really generalizing to unseen data points. Or if this is a very small number, then it means that I'm really generalizing to unseen data points. So this is called the generalization gap. And the goal in most statistical learning theory is to upper bound this quantity by some computable upper bounds. So if we can come up with some upper bounds for this quantity, then I can combine it with this, and then I can at least numerically compute like the bound on the population risk, which is the most important quantity in this context.
I'm sorry, but it seems that there are too many unknowns right now, right? I mean,
Sorry?
there are too many unknowns, right?
In terms of?
For instance, the distribution, do you know the distribution?
Yes.
You assume that you know.
But then the good thing, for instance, like coming to that, for a fixed W, so let's say we fix the W. So W doesn't depend on data for a fixed W. This is a random quantity, right? Because we are assuming the data is random. So if you take the expectation of this quantity with respect to the data points, so if you take the expectation of R hat and W, well, the expectation is again taken over mu z, right?
You get
Mu z n, yes, true. Mu z n. Sorry about this notation. So what does this give us? Let's do this.
It's on W.
Yeah, because W is fixed.
Yeah.
W is not dependent on the data. Yeah,
Exactly.
yet.
That's the crucial. Okay, so let's take a look at this. So let's say W is fixed, is deterministic, doesn't depend on data whatsoever. So what is R hat and W? This is 1 over n sum log W Z I. So if I take the expectation of this, the only randomness is coming from the data points. So this would be 1 over n sum, and the data points are independent. I would like,
It doesn't matter that they're independent.
yeah, true.
It's the sample mean. So it's an unbiased estimator for our job.
It's good to have in, like, I don't know, I just wanted to repeat it.
Sure.
Okay, so what is this thing?
W.
It's the population risk. Then the expectation of this is just RW. So essentially, with this condition, and like with this formulation, then we essentially have here a random variable, and then we want to measure the deviation from its mean. So now, like, we can try to use some existing tools from, I don't know, probability and statistics to estimate this quantity. And then the generalization gap essentially will be handled by this way. And then here, okay, so I was trying to come back to the fact that we don't know music. So even if we don't know music, so this is again like a very structured problem. So because like this is just a random variable deviating from its mean, and then by putting some mild conditions on the measure, and we can try to estimate this quantity.
Yeah.
So even if we don't know it, there is still some hope. So this was my point.
Yeah, it shows some assumption.
Any questions? So what time is it? We started at 2:30.
Yeah, we run until 3:30, then we have 15 minutes break, and then another hour and a half.
So I stop in 20 minutes.
But you stop at 3:30, and then we have 15 minutes break, and then you have another hour and a half.
All right. So now let's make it like a small recap. So what did we? So we introduced the user, the distribution of data. We defined the population risk, and then we said we want to estimate this, and then this is going to be the main decomposition that we are going to use for estimating this quantity. And then it turns out the quantity that we need to estimate, the quantity that we need to upper bound, generalization gap, is a substructure, and then we can try to exploit this. And now the question becomes, how can we estimate this in a practical setup? So like in the next days, we are going to talk about some optimization algorithms which generate heavy tails. And then we will try to understand how heavy tails can interact with this term actually. So like how can we link this quantity to the tail index of some processes, etc. I'm going to define them properly. But to give you an introduction about how to estimate this quantity, let's just have a simple example. Maybe I should just. Example. So let's take W finite. So we have finite many options in the hypothesis class. And then loss is bounded. Meaning CWZ and WZ smaller than V. Okay, so then in this case, how can we estimate this quantity? So actually, I forgot to write. We will make a further step over here in this decomposition. And then we are going to further up about this by same quantity, but this time I'm going to take the supremum over all doubles. So then in this task, I will try to estimate what is the goal. Estimate sub W W minus I and W. Okay, so let's do this simple class. So this is always the first example in a statistical learning theory class. So I go with the convention. And then here W is fixed. So it doesn't depend on the data.
We know B.
Yes, so let's say we know B. Somebody give us. Okay, so let's start doing this. First of all, we are taking the sum over a finite set. So this is actually max W of the same quantity. And then let's take a look at this. So now this term is random. And then we can only give guarantees in expectation or in high probability. So since we have some randomness data. So let's take a look at this probability. So I want to take a look at the probability that this quantity is larger than some epsilon. So I fix some epsilon and I want to take a look at this. So this event is equal to the event that there exists one W such that this is like this quantity, this like this event holds, right? If the maximum is larger than epsilon, so then there must be one epsilon such that this must be true. Okay, so that this is there exists one W such that this this event holds. Exactly the same thing as saying the union of the events the probability of the union of the event is it clear at this point? Any questions? This should be simple for this crowd. Okay, then I'm going to upperbound this by using a union bound. What's the union bound? The probability of union is smaller than the sum of the probabilities. It's like the subadditivity of the measure. Then this is going to be smaller than W. W probability of minus and the larger than epsilon. So here we use that W is fixed. W was random to W couldn't do this. Okay, now what we are going to do here? So since I assume the loss is bounded, so the average of the loss is going to be bounded by the same value. Expectation of the loss is going to be bounded by the same value. So like that, this is like the mean, like the deviation of the random variable from its mean, and we know that the random variable is bounded. So now, is there any tool that we can use to upper bound this quantity?
Azuma.
Yes, so like we can use thrifting, even simpler. So then, and since W is fixed in this case, now we can just upper bound this quantity as follows. Okay, so the inner term, this one, so if we apply the Hessian default to this, then we obtain sum of W's. And then this is 2 times exponential minus 2n epsilon squared over b squared. So the IID assumption is very useful in this sense. So like we can use this kind of tools, and then it's going to make our lives much easier. This is an extremely simplified case, so it's not going to be useful in any application. But then we are going to use this kind of ideas in the case that we look into. Okay, now this is equal to, since this doesn't depend on W, the cardinality of W times same thing. Okay, so this says the probability of the worst case error larger than epsilon is going to be smaller than this epsilon. And then if I just say, if I just define this as delta, the probability of failure, I just define it as delta, and then rewrite epsilon in terms of delta. So we obtain epsilon equals p times log 2 plus log 1 over delta over n. So I just define this as delta, and then I just solve it for epsilon in terms of delta. So what does this say? So let's just rewrite this. This is the convention. We say that the max, the worst case error is smaller than this quantity, b log 2, it's not visible anymore. Log 2 W's cardinality plus log 1 over delta over n with probability larger than 1 minus delta. Okay, so this is our first theorem. Any questions?
If W is very large, probably will not help you a lot, right?
And in the practical case, this set is going to be uncountably infinite. So like this is not going to be applied, not going to apply directly. But then we are going to use this. Let's just give a hint, another like a teaser for the next days. So let's say we have, let's say this is our W. It's uncountable but bound. What we can do is cover this by some sets. And then the number of like the sets in the covering is going to be finite. So we can still come back to this.
It can be still very large, that will depend on various
Exactly.
combinatorial
It
dimensions.
depends on dimension, and then this is going to be very interesting. The dimension will depend on heavy tails. So this will be the surprising bit the next days. Any other question? So I think let's take a break now because I will start at this time after this point. So again, let's come back at 45.
Everything's working fine.
I'll see with you finally. So many.
I've seen it.
What's his super?
Right now I'm fine, sorry. Yesterday I was not.
Choose the American.
The moment I realized
I'm from the Netherlands, like, more used to the Europeans.
You want to take off
I enjoy this. It's good to, because I'm a Soviet Union.
Well, there's a wine reception roughly that time. So we have a reception. You can if you want.
The previous one was, I think, now there is one and a half.
Well, any grandmaster.
Science is good.
I think 45, 50 minutes, and then you kind of get lost.
So if everything is bounded, can I ask you a question? Can I ask you a question? So the conclusion of this first part is everything is bounded, we have a good bound.
Not necessarily. I mean, like this can be unbounded. We can still have a good bound.
Yeah.
The take-home message is like if W doesn't depend on this stuff, then it is good. But then it's a bit
Okay.
stupid
Okay.
because your W has to depend on your training loss. Otherwise, it doesn't make sense.
That's fair.
Okay, so in this part, I'm going to talk about this one. So I'm going to define some things about neural networks, but we will never use them. So I'm just going to define them just for the sake of, I don't know, general knowledge. In case you're interested, I'm not going to spend too much time, but I think it's still interesting to be cover more areas. And actually, like this is going to be the main motivation why I'm going to talk about the rest of the things that I will talk about. So let's just define what is a fully connected neural network. So who is familiar with neural networks? So neural networks are essentially a parametric family of hypothesis classes, right? So like a family of parametric hypothesis classes. So each HW, if you remember, this was our function to predict the labels, has this form. So we first take X and then we multiply. So if you remember X, it's typically RP. It's a vector. And then we first multiply this vector by some matrix, W1. And then we apply a function, nonlinear function, which is called the activation function sigma. Activation function. And then we multiply the result of this by another matrix W. This is a two-layer, fully connected neural network.
And you don't have a bias.
Perfect. This is a fully connected neural network with no bias. Yes, exactly. So let's first define like some of the things, and I'm going to mention bias as well. But the bias is now thought about like not producing much difference in practice. But I mean, we are not going to use this anyway, so I don't care if there is bias or not. Okay, so first of all, let's talk about the activation function. So the activation function is typically taken from R to R. So since this is a vector, the notation indicates you apply this like one-dimensional function to every component separately. Right, so like this is the notation. And then usually like some, I mean, historically, the sigmoid was the most common activation function. You are familiar with it. But then nowadays nobody uses sigmoid anymore. So similarly for tanh, so they were popular but not anymore. So nowadays the most common one is called the rectified linear unit. Rectified linear unit. And it's essentially sigma x. Sigma x is an R. Sigma x is max 0x. So it's this function. I don't know why it has this fancy name. So the rectified for this. I don't know. And also it has an abbreviation called ReLU. And it's also like E is small, very big. Okay, so this is the typical setup. And this one is like two layers. So here we say this is the first layer of the network. This part. This is the first layer, which is closer to the data.
I'm sorry, but you would think that the more smooth the sigma is, the better, right?
In terms of what, for instance, why would you
So
say that?
optimization.
So you can optimize it, that's true, but then the thing that you find might not be better in terms of prediction. Right, so like in practice, there might be a difference. So if you put this, I mean, this is not a differentiable function, etc., but like practitioners don't care about this kind of things. So they just put this and then give it to some automatic differentiation. And then they look at the result. If this is good, they use it. If it's not good, they don't use it.
Fair enough.
So mathematically, this makes more sense. It makes everything bounded, smooth, etc. But then practically, this gives you the application you use on your phone.
But you probably want to add something like at the end, like argmax or something, right? Sort of.
Why would you put argmax?
Well, you want to use some, you want to classify things, right? So for example, you don't want the output, just to be of this sort, like emit sort of huge vector, right? You want a number, like a 0, 1, right? Something like this. Minus one.
I'm a bit confused, sorry. So are you saying this is good or not?
No, I'm saying that people typically at the end, if you want to say it's a dog or a cat, right? So this is, you don't want this, right? You want like something, right? You want so this to be, you know, want to do some at the end, like argmax, whether something is better, a dog is better fit or a cat, right?
But then this is, I'm a bit confused by the comment. So there is no optimization at this point.
Right.
It's defining the predictor. So why would there be an argmax?
Well, this is okay. That's all right. Sort of gets that. I would typically think that this is not the predictor would be 0 or 1, right? That would be.
I see what you mean. So like if you really want to have some prediction at the end, you are saying like it should be
Some number at the end, right?
But then that sigmoid might be even more useful because like if the input is large, it gives you 0, 1. So I'm not sure. So
Okay, all right, okay.
Yes.
Okay.
Just for clarification, is sigma from R to R or RP to RP?
So this is again the
W is a
conventional notation.
W is a
Sigma
matrix.
R to R,
Applied
but then
component.
if you give a
Term by
sigma,
term. Okay, it's applied component wise. Yeah, thanks. Yeah.
this would be sigma E1.
All right.
sigma E2.
Okay, sorry.
And W, it's a pair of W1 and W2.
So right now, yes, I was going to come there. So like we call this the first layer. So we apply the first layer matrix. This is called the weight matrix. That's why it's denoted by W. So the first weight matrix is applied to X. Then we apply the non-negative activation function. Then for the output, we apply the second layer weight matrix. So now this is the second row. And in this case, our parameters are W1 and W2. And if we go back to this notation, this is a small w. Small w is the concatenation of all the W1 and W2. So making it like vectorized, just put everything into the same vector. So what is the size of this vector? Point. So this is RP. We need to define some, we need to make some choices, right? So W1 is in R, let's say D1 times P, and W2, what is the size of W2? So let's say we have I don't know this R outputs. The output of predictor is R many, or let's say just 1 minus 1, 1. It's just 1 times D1. So then the total dimension will be the sum of this parameters in each W1 and W2.
So who is using the same, it's bad taste to use the same sigma for for two different objects.
You mean like you want to use?
Yeah, this one, it's confusing.
Why is it confusing?
Sigma of a number is a number, sigma of a vector is a vector. A vector, the same sigma.
But different.
That's
notation.
It's a notation, so I
That's a
can.
notation.
It's okay. Well, it's okay, you can do whatever you
But
want.
also, let me clarify, in deep neural network literature, nobody's trying to have a good taste. So like this is, I feel like this is
Okay, you agree with me, yeah?
you said like it's bad taste, I completely agree with it. This is what they use.
It's like the Einstein convention.
Object-oriented notation.
Are these videos going to be published? So can we just put some beeps? Okay. So this is a 2-layer neural network. So in general, we could have biases too. So what would the bias be? So instead of, so right now the first layer is W1 times X, right? So we could just replace this by W1 times X plus some vector B1. So then there will be some offset we could allow. And then this would be a parameter 2 that we would need to learn. So then in this case, the network would look like HW of X would be W1 X plus B1. So then you apply the sigma afterwards. So then you multiply this with W2 and then you add B2. So these terms are called biases. And then, but in practice, you can just like ignore them. In my experiments, like they have no, I mean, they are not changing anything. Okay, so this is a two-layer neural network. And we can generalize this easily to any number of layers, essentially. So then we can just define, for instance, N-layer neural network. So in this case, HW would be, we start by W1X, so I'm ignoring the biases. We multiply by W2, but this time we don't stop. And then we continue on to WN. Okay, so then this is an M-layer neural network. And the parameter W will be the combination of all these waveforms. Okay, so this is, any questions about this? So given this model, say deep learning means you are using a neural network, but the number of layers is high. So then it's a deep neural network. So like if you see deep somewhere, it comes from the fact that like there are a lot of layers. So given this predictor, now going back to our original framework, just to remind, our training, so we had like two goals. First the training, and then we will try, the second goal is to estimate what will be the population risk after obtaining a parameter from training. The first goal, training, is essentially minimizing the empirical risk, right? So W in, so this time I'm going to not restrict, like my parameter set, my parameter space is going to be RD in this type, so I'm not restricting the space of parameters. And then I will try to minimize 1 over n. I want to n. The loss evaluated at every data point z. Okay, so now somebody gives us this optimization problem, and in practice, so how, like, what would you suggest to solve this problem? Like, if I tell you this is our problem, what kind of algorithm would you come up with? Yeah, so it's some gradient type method. So now let's, I mean, if you're a numerical analyst, so I gave this talk to in the math department where I graduated from, and there was a numerical analysis professor, and then he almost like fought me because I was trying to use gradient phase method. So like, are you out of your mind? Like, there are all sorts of like different tools generated, and you are using the stupid thing developed in '50s, and yes, people use it. So, but then, okay, so like finally we are going to use a gradient phase method because everybody is using it. Okay, so this, like this part is, I know everybody is, like most people are familiar with this, but just to set the notation. So gradient descent. So the gradient descent recursion is extremely simple. So we initialize some W vectors from W, 0, and then every iteration take a small step towards the opposite direction of the gradient of the empirical risk. So simple gradient descent. So here is like given the data set, there is no randomness in this. And then if we, so this is called the step size. But in the neural network literature, people call this the learning rate. You read the paper, this is learning rate. And if you write down the gradient of this empirical risk, so this way, essentially equal to 1 over n, I1 to n, gradient of the loss, W z. So this recursion essentially tells me I need to compute, like at every iteration, I initialize W from somewhere, and then at every iteration, I compute the gradient of the empirical risk, which is the sum or the average, however you want to define it, of the gradients coming from individual data points. And then I set a small step size, and then I keep this recursion over and over again, and then hopefully it will give me some nice point. So first of all, like in the case where we are interested in, like where we use neural networks, this loss function is going to be completely like super non-convex. So it is very hard to get any like optimization-based guarantees for this procedure. But then in practice, it works really well. I mean, maybe not this specifically, but like the variance of this algorithm. So that's why practitioners are still using this, and then the simplicity of this algorithm is also quite charming because you only need to set this parameter, and then there's nothing else to set essentially. So there is one problem with this specific case, the gradient descent. In the case of modern machine learning problems, is that at every iteration. So first of all, just remember that like W lives in RB. And this D can be easily becoming of order of millions. 10 to minus like 7 to 9 something like this. And it's very easy. If you are using a neural network like this can be super large. And also the data sets are nowadays quite large. So the number of data points is also super large. So you can have like in a typical data set, you would have like 100,000 samples. So at every iteration, this recursion tells you to compute the gradient of, I don't know, a 10 million dimensional parameter, and then you need to sum it over, I don't know, 100,000 data points for every iteration. So since this is like extremely heavy, so people decided to use stochastic algorithm of like gradient descent, where we approximate this full gradient by using a stochastic gradient, which is defined as follows. So stochastic gradient descent or SGD in short. So the idea is instead of computing the gradients over all the data points at every iteration, in a given iteration, we are going to subsample some random data points from the data set, and then we are going to compute the gradient on these randomly chosen data points. And then this is going to be the gradient that we will. So first of all, we will fix a number b, which is much smaller than n. This is going to be called the batch size. And then we will compute a stochastic gradient. So we will first define a mini batch, omega k, which is a subset of 1 to n. And the
Is it
size
possible
of,
to use another instead of B?
sorry.
B is bias and B is
So let's forget about this now. So it's a different b. I mean, there are so many things to define. So pigeonhole principles.
remove it.
Okay, so b is different than everything else now. So b is a number is an integer. Okay, so first we define the mini batch. Mini batch will be the random points, random data points that I choose at iteration k, and then I'm going to compute my gradient over these randomly chosen points. And the number of points in this set is going to be b, this number. And given this quantity, I'm going to define the stochastic gradient as, so I will put the tilde on top of R, and I'm going to index it by k. This means the iteration. This means this is stochastic gradient. This will be equal to one over b I in omega k. Omega is over there. The gradient of loss W let I. Okay, by using
I'm
this.
sorry, I'm again confused.
Sorry.
So your omega
Mhm.
depends on time. For any k, you choose omega k, or is it different? It's
At every k, I choose a new omega k. Yes. It depends on time. So let's say I have like a bunch of data points. At every iteration one, I choose like some random points. I compute my gradient on these points. In the next iteration, I choose a different part of the data set, random, uniformly random. And then this is going to be like the choice is going to be random, such that for all k and for all fixed w, if you take the expectation over omega k, the gradient of, we are going to want this as a property, the gradient of RKW will be equal to the gradient of Rn and W. So if you choose omega uniformly randomly, then you can immediately have this property. So this is called the unbiased gradient. So unbiased stochastic gradient. Expectation over complicated.
Well, it's having the subscript omega k. You just say you take the expectation over omega k, but omega k is a random sample. Shows the uniformly.
So omega k is a random sample, random subset which is chosen without replacement, for instance. Let's say bit replacement to be.
to keep ID with the replacement.
Sorry?
To keep the same it's replacement to, you may take the same one. Yeah.
Yeah, you can take the same one.
And it doesn't make any difference.
It makes difference in the variance of the estimator, but for our purpose, it is, we don't care about this for now.
So the reason I'm saying is you're actually taking the expectation over the law of omega k. You're integrating out the law of omega k, or not?
And yes, but this is conditional W. I don't know if this is your confusion or something. Okay, sorry. Yes, we are integrating over W, omega. Is it confused? No, I mean, it's a
Yes,
very simple
so,
concept. Sorry,
the
if it's
problem is
confusing, it's my fault.
I expect to see the random variable not be a subscript.
This is just like a notation. I don't know. Just imagine like there's a distribution of omega k is the same distribution for every k. So then, would it make it more clear if I just replace it by the distribution but not the random variable? And I'm going to write this as well.
No, you put a condition on omega, yeah? You put conditioned on omega k.
No,
No, you integrate out.
It's not conditioned on omega k.
Precisely. Low of omega k. I'm taking the expectation over the low.
Then how can it be random?
The law is
On the right-hand
uniform,
side.
Omega k is right hand side is fixed for
It is uniform, yes.
just
The
expectation.
data is uniform?
Yeah.
Yeah, but if the data is random, the right hand side is random.
So fixed W, fixed data set. Okay, so I mean this everything is random, but the randomness comes from different parts. So if we fix the data set, so and if you fix W, this is not a random quantity, right? So just what I'm trying to say, I'm sorry to make this extremely confusing. I'm trying to say you can choose, you can compute the stochastic gradient such that on average over the choice of stochastic gradients, you can get the true gradient that you want to compute in the first place. This was my goal, but I made it a bit more complicated. And then for every fixed K, W, and S, you take the expectation of this quantity over the randomness coming from the sampling, then it gives you the gradient with respect to the gradient of the empirical.
To make it simple, take B equal 1 and it's okay.
Yes. Should I do it now? Or what? Okay, now we have two hyperparameters. So, okay, so now if I use the stochastic gradient in this recursion, I will just have WK plus 1 or WK minus step size and the gradient of the stochastic gradient. So now we have two hyperparameters, step size. And then the computation of this, we have the best sense. Okay, now I'm going to define the problems that we will be in the next days. So I'm planning to finish in 15 minutes, okay? So if you report that. So the question that we will try to answer. So there are some observations. First observation is this. So let's say you use gradient descent. Gradient descent is the case where you use all the data points for your gradient computation at every iteration. So this would be like the idealized case because there is no additional error coming from the stochastic gradient. But it turns out, even though it can give you some good training performance, so you get a low empirical risk. If you look at the population risk, if you evaluate the output of this algorithm on unseen test data points, which we call the test performance, it gives you very bad, it gives you bad test performance. So you train it by using the full data points at every iteration. It finds a good point in terms of the empirical risk, but if you evaluate this thing on some other data points, the performance is not as good. And if you do the same experiment with SGD, you still get good training performance. So the empirical risk is close to 0. Lots of cases. But then this time you also get good test performance. So then what's happening? First of all, this is like quite counterintuitive because in numerical analysis, like this is supposed to be a bad version of this algorithm. So you are putting more error in this one. And then finally, it is giving you something more practical. This is like quite counterintuitive. And so what would be the reason of testing? Okay, the second thing. if you look at the generalization bounds, the current generalization bounds, if you remember, the generalization bounds are error bounds on the generalization gap. If you look at the bounds in the literature, they typically behave like this. So the generalization bounds typically behave like square root of b over n. In expectation or in high probability, etc. So d is the number of parameters and n is the number of data points in the data set. So for a fixed d, the error goes to 0. But then there are some experiments which show this. And let's take a look at how the error behaves. I mean, this I'm going to sketch this, but this is a real plot from the paper. I have to give you the reference. So in this paper, they wanted to see how the training and test error behaves as they increase the number of parameters in a specific neural network. So they fix a neural network, they train it. After the training, they look at the training error and the test error, and then they increase the number of parameters in the network. They do the same thing, and then they have like plots for training and test errors, depending on the. So this bound essentially tells us that if you increase d, your test error is going to increase. Point. But then in this experiment, which was done on.
So the y-axis is the test error here.
So there will be two plots. I'm gonna write them. So like first, if you look at the training error, it goes like this. But this makes sense, right? So like as you increase the number of parameters in your network, it's going to be more powerful. It can fit to the training data in a more easy way. So as you increase the dimension, the training error is going to decrease. But then what is more interesting is that if you look at the test error, it also decreases like this. And it doesn't increase after some point. So the distance, which is the generalization gap, doesn't increase with t. So as opposed to what the current theory suggests. And then this is a big mystery, like why this is happening. Because like as you increase the number of data, a number of parameters in your network, then you are searching in a much bigger space. And it is quite confusing why this is not happening in practice.
Generalization bound is very crude when you compute it, isn't it? The bound.
Something is wrong. This for sure. So I mean, like this is like at least the assumptions or the framework, something is not matching this for sure. And then like the question is like, what is wrong or what can we improve or how can we reformulate the question and then analyze it such that what's happening in practice.
Sorry, being stupid, I'm not, what's the issue with the gap? Is that it doesn't decrease after a while or that it doesn't increase again or?
The theory says the gap is should increase with square root of d. So let alone increasing, it's usually decreasing. So then, I mean, not, okay, it's not decreasing, it's not increasing. So like it just converges to some number and then it is not really obeying what the theory is saying. So
But
I mean,
isn't-
this is an upper bound, so this is still true. Sorry.
Is that paper with GD or SGD?
This one is with SGD. You have a question?
Yeah, I was about to say something stupid. The training performance and the test performance, you're just taking the data from the same distribution, right? In order
Yes.
to train and then to test, and then the performance is measured the same way.
But it's not the same data, right?
Well, but
Same distribution. Same distribution, but then the bound is also for the same distribution. The bound also exploits the same distribution.
okay, because
I mean, this is a mystery. So like it is still not, I mean, I'm not going to be able to provide a full-fledged solution to this. Like there is a lot of people working on this. But then my solution to this is that this reason is due to heavy tails. So now we can connect this to the picture. So I'm gonna claim that this generalization bound is not going to scale with D. It's going to scale with some intrinsic dimension, and this intrinsic dimension will be depending on the some sort of heavy tails coming from the optimization process. So, any questions?
Maybe just a stupid question, but if that bound is for GD,
So these bounds are quite generic bounds. So like it doesn't really take into account the algorithm structure. That's one of the reasons why they cannot really capture what's the. Yes.
Maybe it's not the right time for this question, but somebody over lunch told me that training a neural network costs $10 million in electricity. And so maybe we should listen to your numerical analysis professor and do it in a cheaper way.
I mean, do you think like my numerical analysis professor who has no idea about machine learning has a good, better idea?
Maybe we should find one. I don't know. It's just if people say it works good in practice, but then also people say only Google can do it because it costs 10 million in electricity. So like something that works good in practice is not to me the same as something that only Google can do. We should be able to do it as well here. But okay, this is why I'm saying I'm not sure if it's the
I think your question is for the wine session.
yeah, maybe for the right session.
I'm too sober to answer. On camera. And it's beyond my scope.
I'll ask after a couple of wines. Yeah.
Depends the scope. Okay, I'm going to like just hint on where the heavy tails would come from. And then I'm gonna stop here. Tomorrow. I mean, can you any idea like where heavy tails might arise from stochastic gradient descent? I don't know what I missed in today's morning lectures, but I know this. Okay, so I just want to write down
outliers,
not outliers, like you just apply stochastic gradient descent without any outliers, and you can generate heavy tails.
So without any outliers in the
No.
space. Oh,
In which space?
uh,
Not the space or? Not the space, like it can be just full Gaussian. Okay, so I'm just going to hint like teaser. Well, actually, I'm not going to talk about this line, but just to show you like the source of heavy tails. So let's say we have the population risk problem. A transpose W minus B squared. And the expectation is taken over the law of A and B. So A is a Gaussian with zero mean identity covariance, and let's say B is a Gaussian. We don't really care about the parameters. Okay. So this is our optimization problem. I don't know any other thing, simpler problem, obviously. For linear regression with Gaussian data quadriticals. So let's say we use SGD, but in a different way. So WK plus 1, WK minus step size times the gradient of 1 over B. This thing, sum I want to be.
Is B now the same as B or different?
Oh my God. Okay, so let's just make this cube. Sorry about this.
You are very biased towards me.
This is not the bias. Did I make more mess? No, to be honest. Okay. So I'm going to assume at every iteration, I observe a new sample from this distribution. So like I don't have a data set this time. So at every iteration, I'm assuming I can draw a new sample from this. Let me see. So then we will have, okay, I'm going to denote this is I k plus 1 transpose k minus 2 I k plus 1. So it's every iteration I draw B samples and then I compute the average and then I take the gradient. Is it clear? Okay, so now if you make
But you're taking the gradient of that thing square, right?
You want to square it.
also with parentheses.
Yes.
You're not doing empirical risk minimization at all.
It's not empirical. I'm just saying, okay, let's
Intuition.
just take this problem and then assume that at every iteration you can get B new data points. Okay, so then. So if you take the gradient with all the arrangements, okay, so let's put the one over here. It looks like this. Identity minus step size to batch size. Find out to be AI k plus 1 AI k plus 1 transpose. Okay. Plus step size over batch size. I want to be AI k plus 1 Q I k plus 1. So I just did some terms rearrangement. So I took the gradient. The gradient is simple, and then I made some like there's a term which contains the k, and then I took it to the parentheses of identity minus this, and then there's an additional term. So I can define this. Okay, so this is now a random matrix, this one. So I can define it as capital MK plus 1. And then this is a random vector. Let's call this
Theta.
theta k plus 1. So it turns out our SGD recursion is essentially WK plus 1 equals some random matrix k plus 1 and k plus 1 WK plus theta k plus 1. So there is a huge literature about this linear recursions, and then it is well known that under some conditions there exists a unique positive alpha such that the expectation of MK, so this is an IID random variable now, IID random matrix, to the power alpha is equal to 1. And limit T to alpha probability U trust or let's just start this way. And W infinity larger than T is not triggered. Okay, what does this say? Depending on the moments of this matrix, which depends on the data, which depends on the step size, batch size, there will be some alpha, and then this alpha is going to be completely determining the tail properties of this random process in this stationarity. So W infinity means it's the stationarity. So if alpha is smaller than that, which can happen very well, then even though you are using Gaussian data with a super simple optimization problem, your recursion can generate variables which have no finite second order moment. So this is because of the multiplicative noise. We are multiplying the noise with the iterative stuff, and then it can immediately blow up some of the moments, and then we can end up with random, like random variables in the stationary. So then, since this is the case, I'm going to argue that this kind of behavior. So if we have like heavy tail iterates coming from SGD, this can have an effect on the generalization bound, and then I'm going to argue how it can be proved.
So this is a discretization of an SDE.
This time it's not a discretization. So this is the true recursion with no data set. So like at every time you are getting a new data point, but there is no discretization at this point.
Okay.
Is T the number of iterations?
No, T is this.
But you're right.
Some
Over there it is. It's a different T's. You have
Did
two
I
different
do T
T's.
somewhere else?
Yeah, you always do that. Or there is a K there, a T or something.
So K is the iteration.
On the right hand side, on the other board, other
Did I
board.
use T here?
There is WT plus one or something, WT or something.
No, it's always K.
It's okay.
That's okay.
K. So
We forgive
I
you,
made a
that's okay.
mess, so
Yeah, but
so this time I didn't.
yes, this is a number of calculations.
What is the normal MK have raised to the power of alpha?
It's not an internal, no induced to Yes.
So basically, to rephrase it, it's like you show that the optimal solution, or like the solution converges to something that looks like something that's heavy tailed, the best parameter.
I mean, it's not the solution, but then
The steps.
the distribution of the iterate is going to converge to a heavy tail
Yeah,
distribution.
but W is a parameter essentially, right?
Yes. What's the question, sorry?
No, I'm just rephrasing it to just make sure I understand. Like, so you're looking for a good parameter to fit your model, which is W, and then you say, if you do this recursion, if you do this SGD, you got your parameter after many iterations will look like a heavy tail, basically.
Yes, so at least the norm of this W can be very large, some non-negligible.
So alpha depends on W.
Sorry,
Alpha is the same in sensitivity to initial value.
alpha is,
You start W with something at time 0 at any point.
there's no alpha, right?
No, you start from W, yeah, from initial point.
Yes, W0.
And so this statement doesn't depend on initial value. Yeah.
So under conditions, you can show that this is like an ergodic process, so it doesn't depend on the initial point, and that this is the station, this is the W in the stationary. So that I mean, you can show there's a
Stationary version, yes, it's a Markov chain.
Yes, so this is a Markov process,
And it has unique station distribution, and
and then
this
this
has.
is one sample.
Yeah, okay,
This is this.
okay.
This condition on the norm of MK. Norm is 1 to the power alpha.
This is not a condition, this is then, so under conditions, then there exists this.
And this for every K, this one.
So at every K, this is an IID, so like you
Yes.
just write.
Are they the
one.
same?
M's are IIT.
They're the same, even though they're different number of summons. Oh, no, they're the same number of summons.
Yes.
I see.
So in a sense, this is drawing from the fact that you can have A and Q at every iteration randomly. So in a sense, does this, so if you come back to the original process perpetuity, does this mean that the mini batch size has to be small relative to the size of the data set?
I mean, that's a great question.
Dependent.
In the case when you have like finite limit data points, it's very difficult how heavy tails can emerge, but then we published a paper, we show that it's going to be more and more heavy tailed in a way. So we can talk about it.
So, I mean, here you take IID coefficients, yes, every time. But you could take that to be an ergodic chain, the coefficients themselves. And then you would get a result like this also.
No, it's clear, it's unclear why it's ergodic. It's not a Markov chain anymore.
No, but it's this, the coefficients are drawn in an IID way, this
Yes.
AI K.
Yes. If you replace by what? You want to keep Markovitch or what do you?
You need, it's a b-dimensional thing, so, right?
Okay, take B equal 1, okay, yeah.
Okay, take b equal 1, and then you get a Markov chain.
Yeah. So you still have a Markov, now you have, for any B, you have Markov chain.
Yes.
Take B equal 1, you have Markov chain, you have drift towards 0.
Yes.
Yeah. So
Yes. No, but
there is shift, yeah, whatever.
the thing is that the coefficients are IID here, right? So these matrices are all IID,
Yeah.
what I was asking about. But they could be a chain of matrices.
I'm not sure. So the thing is, like, to
Which-
show this, we relied on other people's results. So this is not that we proved. We just know that
Let's
in
go
this
back
case,
to Keston and then
Yeah.
Goldie and.
Yeah.
it goes to
Goes to, in matrix case, it goes to Keston.
true,
Yes,
but
but
the result that we used by
Sure.
by Asmayer.
I understand what you plan to do.
Here Asma is my, he's now, he lives now.
He was?
He's still in this early sixties, yeah.
Yeah. So like I mean, it's not a very old theorem. Like it's kind of new, maybe like 10 years ago. But then it is not our contribution. Our contribution was to make this connection and then show that all this.
IID, but the distribution is not normal,
but
some finite.
Again, so like I'm not gonna focus
Finite,
on
very
this
large
part
set.
too much. I'm going to argue
Because
that
the
like, these
omegas
heavy tails
are
can
taken-
arise, and I'm going to try to model these heavy tails by using some alpha stable driven stochastic differential equations. And we will try to develop our theory on that.
Right.
So
Yes.
maybe it's a good time to stop now. Any last questions?
Well, again, so it's just maybe really this is wake up example. Yeah, the question is take B equal 1 and take, what is it, dimension equal 1. So you have a Markov chain, which is exponential, geometrically ergodic. Geometrically ergodic, and the station distribution that doesn't possess exponential mode.
So I think most of these.
Interesting.
Depending on
Yeah.
this one, depending on this alpha. I mean, yes, exactly. It doesn't-
Yeah, it doesn't have exponential, so the Markov chain itself, we have geometric rate convergence actually.
Use these.
Okay. Yeah, because drift in that way, you have geometric radius. No? Why not?
Because the invariant distribution is not exponential.
Can't you do?
I'm confused.
No, that's simplified. It is not geometrically.
Because we have this zero drift. Okay, zero drift. Yeah. It's zero drift. Yeah. Because the drift is 0. Yeah, I forgot that expectation of A is A squared.
It is e to the power of a variable which has negative.
Exponent. Yeah. Okay. So we got it. Yeah. Yes, exactly. Yeah. Its logarithm is geometrically ergodic.
Exactly.
It is not geometric.
This morning was still for independent moment, so the socialization should still be independent.
Yeah.
Negative drift.
Exactly. Okay.
And no exponential.
If WK was function of MK and MK.
I mean, we can.
Yeah.
So any last question?
Yeah.
If let's finish now. Then-
Thank you.